All right, so we're keeping on with fluids. Today we're going to talk about pressure. So let's talk about what it is. So pressure, what pressure is pressure is equal to a force divided by an area. Now these should be perpendicular to each other, but that's pretty much always the case. You'd have to do some trigonometry if it wasn't, but that's very, very unusual. So let's talk about units. I think we've done this in the gas, but just to review real quick, this is going to be force, and that's going to be in newtons. This guy right here is area. Area is going to be in meters squared. Nice. P stands for pressure. Pressure is going to be in pascals. A pascal is a newton per meter squared all the time, just like back in the day. Now, a pascal is very small. I mean, it's very small. A newton isn't much, and a meter squared is big. So it's going to be very small. So usually, what we're going to use is kilopascals or even megapascals. Okay, something you should know is atmospheric pressure is 101.3 kilopascals. Just to be an educated individual, you wouldn't have to memorize this for the test, but you should at least be aware of such a thing. It might be on your formula sheet. Let's find out. It is. It is on your formula sheet. They just do 100, but it doesn't really matter either way for that small difference. Anyways, this is pressure. Let's do a practice with it, and then we'll apply it to some fluids. A column of cement has a base area of 0.5 meter. So this is the area. That's the whole thing. If it has a height of 2 meters, okay, so area is equal to 0.5, and it's 2 meters tall, and is 3,000 kilogram per meter cubed. How much pressure is on the ground? Nice. We want to do this one because we want to combine yesterday's stuff with it. So what we got to figure out first is we have to figure out what's the mass, what's the force divided by the area. You got to know force. So we are going to use yesterday's density is equal to mass divided by volume. I know the density. The density is 3,000. 3,000. M is what we're looking for, and we're going to be dividing by the volume. It's going to be the area of the circle times the height, like all your prisms. So 0.5 times 2, doing some quick maths here, M is equal to 3,000 kilograms. That's how much cement is there. So now pressure, notice the P versus the rho, right, is going to equal force divided by area. Your force is going to be 3,000, almost. Don't forget, you got that pesky gravity there. Divided by your area, the area is 0.5. So the pressure is going to equal about 58,800 pascals. Now, to put it in something more useful, let's round it up to 59 kilopascals. So pretty heavy, man. Hey, and that's how you do that one. Now, what we're going to use pressure for is Pascal's law, or Pascal's principle. They're both names are used. This says that pressure in a fluid, because it could be a gas too. In a fluid will be dispersed throughout. Okay, so let's give you an idea about what this is talking about here. So let's pretend you've got a glass of water and you put a lid on it and it was attached. So this was right full to the brim. Okay, there is no air in there. It's just one container of water. Now, if you press on this area here and you press it in just a little bit, you're applying a force, which is applying pressure to the water. Okay, the water is going to be under pressure. The pressure isn't going to be remaining on this area here, it's going to be pushing on all areas of the container. All right. So, and these pressures are going to be equal. The pressure is going to be equal throughout the liquid. All right. This happens in a balloon. If you've ever tried to squeeze part of a balloon, it'll just bulge out the other way because the pressure will spread out to all the different parts in equal fashion. Okay, so that's it. So, one way you can think about is pressure is equal everywhere. So that's kind of what we can take away from it to give you the short version. All right, let's do a problem to practice this. So here's what we got. This is where it's typically going to show up. You've got a hydraulic, you've got a smaller hydraulic here, and you've got a bigger hydraulic here. Now, we're pushing with a force of 10 newtons down here, and it's going to go up on this side. Now, the forces are not going to be equal to each other, but we're going to figure out what's this force here, force X. Now, inside of this, you've got water or some fluid, doesn't matter. It's going to have some pressure. This pressure here is going to equal the force divided by the area. Okay, so here's a force, there's an area. These are, you get the pressure. This guy is going to have a pressure as well. So this is going to equal force over area of this side here. But from the last slide, we know that the pressures are going to be equal to each other. So what we're going to do is we're going to combine these two equations together. So we're going to call this F1A1, and we're going to call this F2A2. Now we can stick them together. We're going to get F1 over A1 is equal to F2 over A2. All right? And this is what we're going to use on these types of problems, all right? Because the pressures are the same, you transitive property them away. Now, this should look familiar to like something like Boyle's law or something like that. Whenever you have a ratio like this, the units don't matter as long as they're consistent. All right, so we can just use centimeters. And then on the top, we could use pounds if you wanted, or whatever unholy unit you can think of for force. So let's set it up here. So we have 10 newtons on the top divided by a 1.5 centimeters squared on the bottom. And that's going to equal X on the top divided by a 4.5 centimeters squared on the bottom. Hey, I wrote the units this time just so you can see. Yeah, they cancel out. It's going to be A-OK. So crisscross multiply sauce, we're going to get 30 newtons for X. Wasn't that fun? All right, let's do another one. So what we got here is we have a handle. Don't worry about all the geometry here. The handle is going to be pushing down with 10. We're not going to worry about torque or anything here. Let's keep it simple. You're going to be lifting a load with some force. You're going to figure out what the force is. You've got a cylinder here. It's 1 inch across here, 3 inches across there. Well, let's see if you can pause the video and figure it out. I'll catch up to you as soon as you unpause. Well, finally you unpaused it here. So let's set this up. So F over A is going to equal F over A. Now these are 1s and these are 2s. Okie dokie. So we don't need to worry about converting to newtons or any of that nonsense. So you got 10 pounds divided by area. Ooh, area, it's a circle. So we're going to have pi times r squared. The radius is going to be half of that diameter. And this one is going to equal f. I'll just call it f because we don't know what it is. Divided by pi times the radius, which is going to be 1.5 squared. All right, multiply, multiply, multiply. You're going to get 90 pounds. Ew, gross. Hey, and that's it. That's all it is. Let's do another one. I like this one. So this one has a couple things. Diagram below shows a hydraulic chamber with a spring. Check that out. So you got a spring constant of 1250. attached to a piston with a rock. We got a rock of mass 55.2 resting on the plunger. The input piston and the output plunger are the same height. Nice. And each has negligible mass, so you don't need to worry about any other stuff there. The chamber is filled with water. All right, in order to maintain equilibrium, how much must the spring be compressed from its relaxed position? Okay, so once you put them on there, how much is the spring going to compress? Well, to figure that out, we got to figure out force. Let's figure out force. So F over A, F1 over A1 is equal to F2 over A2. F1, let's do the rock first. We know we're going to have 55.2 times 9.8 divided by 65, and that's going to equal F, because that's what we're looking for, right? We're looking for this force here, divided by 15. Multiply, multiply, multiply. You're going to get a force of 125 almost newtons. I'm sure it's that way if you went with a 10 for gravity, but we're too good for that, right? Now, we're not quite out of the woods yet. We need to figure out how much the spring is compressing. Do you remember that formula? I hope so, because F is equal to K times X, negative K times X, but let's get real here. We know what the force is, it's 125. We know what the K is, it's 1250 times X. Ooh, tough math, you think you got it? X is equal to 0.1 meters. All right, or 10 centimeters. It doesn't, either way. Does that make sense? Sounds good to me. Let's do the part B. So this time, the input piston drops 22 centimeters. How much does the output one rise? So this one goes down by 22. This one's going to go up because, yeah, it goes up by something. We got to figure that out. Ooh, do you have any ideas? You've done this kind of thing before, but you probably don't remember it. So how are we going to do this? I know what you're thinking. You're thinking of adding up the volumes. Yes, you could do that. There's an easier way. Let's just think about the energies. If the rock goes down, what did it lose? It lost potential energy. If the spring gets squeezed up, what does it gain? It gains potential energy. Spring potential energy. Hey, and those two energies are going to be equal to each other. So your gravitational potential energy is going to be mg, and that's going to equal your spring potential energy, which is 1/2 kx squared. So what we're going to have now is a mass of 55.2 times 9.8 times a height of 22 centimeters. So you got to change it to meters. 22 equals 1/2 times k, which is 1250, times x squared, and that's what we is looking for. Solve, solve, solve. X is going to equal 0.44. So since it says centimeters, we should change that to 44 centimeters. And that's it. Does that answer make sense? Yes, it does, because this is a bigger one. Since it's bigger, it's going to move less. So if you think about this volume here compared with this volume here, these volumes would be equal to each other because the liquid's not going to compress really. But it should add up, whereas since this one's more narrow, it's going to have more height. So you're going to have more height for the spring side of this situation. Nice. Hey, that's it for today. Smash that like button and subscribe.